everybody can hear me, and you can see I'm very sorry for the delay in this talk. As you know, in science is very important that we look for uh, problems, and whenever we are trying to do an experiment, we run into problems. We think everything is covered, but they're not. Like today, I had checked everything in my computer and I worked out that things will work. But the very moment when I was just about to join in, the what happened? As you may have guessed, my laptop hanged, and then I had to reboot it and get it back to there. So now I hope that this system is working, and that is another reason why I am really hope that this is not going to be the normal way of giving talks, because one of the pleasures of giving a talk is to see people, see the faces, see the reaction of of the people, and to be able to interact in a direct manner outside the classroom. And this is not happening here, but hopefully we will get by in the whole thing. You all of you are already into many talks in for the summer school, and a lot of you people would be thinking of what kind of benefit you are getting from the summer school, and I hope that you are all enjoying yourself in the whole thing. But before I start, let me be clear on what happens in the summer school and refresher course. One thing you must take into account is that neither the summer school nor the refresher course is something which uh, we want to uh, is not something by which we want to teach you to do astronomy, teach you astronomy. This is not about understanding or learning about astronomy. There's a very simple reason for me saying that, is that if I calculate correctly, this is my uh, 25th year running, since 27th year running since I have been learning about astronomy, and I don't think I have learned astronomy completely enough. So, in case any of you will learn astronomy with the summer school, which is in a matter of 1 month, 2 months, which would mean that I have been very dumb and you all are very intelligent, and which I don't want to accept that. So, teaching, so don't expect that by attending a few lectures in here, you will be able to understand astronomy, or you'll be able to do some understand details of what we are doing in this work. So the question arises is that why are we doing this summer school and refresher course at all? If you are not going to learn astronomy, what is the point in doing the summer school? The essential point in the summer school is to show that is to advertise astronomy. In a more, it is that for some of the summer school students who are about to start their careers, the idea is that there is this exciting field out here called astronomy, and we would like you to consider it as an important option for your future studies. For the people who are taking the refresher course, and we would like you to be aware that there is certain thing like astronomy happening in this, which may be different than your field of interest, and we would like to share the excitement that we are doing for astronomy and not necessarily teach. So the first talk I'm going to give you right now is nothing to. I don't expect to give you a lot of information on subjects. What I would like to do is tell you why people like me have spent 27 years or trying to understand astronomy, and why do I come here every day in the morning, sit down, try to get my computer up, try to look at the horrible data which I cannot understand at all, and spend my time doing all this work. What is this real madness is something we should talk about. One of the reasons which I personally have been fascinated with since I was very young and I started doing astronomy, as you may understand, is a natural subject called black holes. And one reads this standard books by Stephen Hawkins in our times, and now there may be many more books on this subject. But and one gets intrigued. What is this thing about the space time, and what is this thing about space time being curved? What is this thing about this extremely exotic objects? How do we actually get to get knowledge about them? What is it happening? That is what intrigued me. However, as soon as I entered the field, I realized that all the things which I had read about, or heard about more specifically, or glanced through, were nothing compared to reality. Reality was much more bizarre, it was much more difficult, and it is much more non understandable than anything which is given in the books. It is much more non understandable than all the complicated theories of Einstein which have been put forward. And the, the, the most interesting thing is not that we understand these things, is that how much we do not understand and how much is left for us to figure out what these things are about. So, in this talk, I'm going to talk to you about black holes. I'm going to start with I start with a very brief introduction to tell you what are black holes, which you may have heard before, but let me do it in my own fashion. Now, I want you to do imagine things. Imagination is important in science. So the first thing I want you to imagine is that you take something like this sun and you squeeze it. And if you squeeze the sun, let's say the sun is a very big object in the sky. But suppose by some unknown means, I squeeze it. I squeeze it so that it becomes as small as 1.5 kilometers in size. By definition, that object which will form if I squeeze the sun to 1.5 kilometers will be called a black hole. So the first thing I want you to take from this talk is that black holes are small and they are dense, right? So if I form a black hole from the sun, it will be very small. It will be only 1.5 kilometers long and it will be dense. Because it is small, and as we know that even in Newtonian gravity, the gravitational force is given by gmm by r square. Now what we are doing is we are keeping the mass constant, the capital M constant of the sun, but we have reduced r and made it much smaller. So the gravitational force has become very large on the surface. So the black holes have very powerful gravity. So there's simply three things. Black holes are small, they're dense, and they have powerful gravity. Right? Now, the idea is that the gravity is so high that even light cannot come out of a black hole, which I will explain a little bit in a while. And because light cannot come out of a black hole, nothing can come out of a black hole, because we know light is the fastest thing and nothing can travel faster than the speed of light. So nothing can come out of a black hole. If nothing can come out of a black hole, no information can come out of a black hole. And therefore, the surface of a black hole is called an event horizon. Horizon is because, as you know, the horizon is beyond the horizon, we can't see anything. So that is why the surface of a black hole is called a horizon, because we can't see anything beyond that. It is called an event horizon because all the events which take place happen outside the black hole. For example, like you are hearing my talk, you can go and tell people that you heard my talk or did something that. But uh, if you were inside a black hole, you could never tell anybody outside a black hole that you heard my talk. For people outside a black hole, no events have occurred inside. So in fact, we can only see events which are outside a black hole. Therefore, the surface of a black hole is called an event horizon. So anything happening inside that is completely unknown. Now, what does it mean that light cannot come out of a black hole? And let me explain that a little bit better so that you uh, understand it perhaps in the right way. If you are sitting or standing close to a black hole, you're not inside a black hole, no? You are standing outside, but you are close to a black hole, and you have a torch. You shine the torch outside, I mean away from the black hole. So you're standing outside a black hole and you're shining the torch away from the black hole. Now, if your torch has a blue color and it's going away from the black hole, the light has to work against the gravity of the black hole. And because it has to work against the gravity of the black hole, it will lose energy. And what do we mean by losing energy for light? It means that the light's wavelength will become longer or the frequency will decrease. So as I shine a torchlight, I'm standing outside a black hole. I shine a blue torchlight outside. By the time it goes far away, that light would have become reddish in color. This is called gravitational redshift. So now I'm standing at a distance, some distance away from the black hole, and I'm shining this torch, and my blue light has become red. Now, if I come closer to the black hole and do the same experiment again, I shine that light again, and it goes far away. It will become more and more redder because it has to work harder against the gravity. And as I come closer and closer to the event horizon, remember I'm still outside the black hole, but I'm going closer and closer to the black hole, closer and closer to the event horizon. And as I shine the light becomes redder and redder and redder till as I approach the event horizon, the light will be so reddened that any light reaching in the far away will have infinite redshift, which means it will have lost all its energy. So since so any light coming from close to the event horizon would lose all its energy by the time it comes to far away. Therefore, in this sense, what we mean is light is can never come out of a black hole. So a black hole is black in that sense. In this talk, this is all that I'm going to talk to you about black holes. And there's a reason for that. The reason for that is I'll ask the question, can black holes exist? And the reason for this, why uh, this idea about all these black holes was not considered important, is when in as you may know that in 1918, more than 100 years ago, Einstein proposed his general theory of relativity. And quite a few years later, uh, a person called Carl Schwarzschild, who was a soldier, you know, did some mathematical calculations and said that if Einstein's equations are correct, then something like this is what will happen if there is something like a black hole. But nobody took it very seriously. Nobody was interested in black holes at all. And the reason for that is the first statement I made. The first statement I made was, you imagine that you take the sun and then you squeeze it to 1.5 kilometers. Now, how can it ever happen? How can a big thing like the sun be ever squeezed to such a small density? If that can never happen, then why bother? Science is about reality. It is not about what we can imagine and all. So some people decided to imagine things and work out the mathematics, but most physicists were not interested in this question, and black holes were not considered interesting at all for a long time. This whole thing changed when a young man was taking a ship from those days Madras to England. And in that ship, he made calculations, and that calculations were astounding. His name was Chandrasekhar, and what he found from his calculation was, yes, it is possible under certain circumstances that if you take a very big star like a sun, and under certain circumstances, it can start to collapse. And when it collapses, it will form a black hole. Thus, Chandrasekhar has answered a very important question. Can black holes exist? And he said, yes, There is a way by which black holes can form. This was revolutionary, and a lot of people protested against it. And Sir Eddington was particularly against this theory for various reasons. But however, apart from a few group of people, you'll be surprised to know, not many people were still interested in this subject at all. Okay, the reason for that is, can black holes exist is not an important question. It's not the important question. The most important question is, do black holes exist? You see, if something can exist, does not mean that it will exist. And if there are no black holes in the universe, and for some ways, like Sarrington was saying, that black holes will never form, and Chandrasekhar was correct, but nature will have its way to stop them, then there is no way and no interest in studying these kind of objects, at least among the physics people who are not involved in the mathematics part of the subject or just in imagination. The answer to this question, which I put out in red, do black holes exist, is of course yes. And now, 100 years after Einstein, we can answer that question, and yes. However, we started answering this question only in the 1970s, and it took us 30 to 40 years to answer this question. And now we have definitely answered this question, and we know that it is yes. So, for the rest of my talk, I am going to not give you a talk anymore, as I say. I will be more like a lawyer, and I'll give you evidences. What evidences we have to know that black holes exist. In some sense, I will tell you a story or a sequence of events which happened from 1970s onwards to about 2010, 2020, 15 now, which helped us answer this question with a resounding yes. We are now very, very sure that black holes exist. Now we will turn this into a kind of a court case, so I have to prove that black holes exist. So you will be all the judges, and you have to choose whether all these evidences which I have put forward is real or not. Now, if you want to answer the first question, like can black holes exist, like Chandrasekhar, you have to sit in a table and desk and write equations and try to find out things about it. But if you want to ask the other question, do black holes exist? You can't do it on a pencil and paper. You have to go and look for them. And since there are no black holes in the Earth, or at least we have not found them, you have to look for them in the outside universe. So let's take a look at the outside universe. On the left side of this image, you see this one. This is a map of the sky. You see, it's funnily shaped like this because when you look up into the sky, you see a dome. But we want to represent this dome in a piece of paper. So the way we do it is we make it into this particular shape and represent it like that. So this is the kind of representation of a sky if you look up into the sky and you see it. However, this is not the sky you can ever see from anywhere on the earth and from any time. The reason is, even this sky, this is what you would see if our eyes could see X-rays. And in fact, even if our eyes could see X-rays, you will not see this because the Earth's atmosphere absorbs all the X-rays which come from the space. Sorry. And that is a very good thing because X-rays could be harmful for these high energy particles could be harmful to us. So the atmosphere of the Earth protects us from that. However, if we want to know what kind of X-rays are coming from the universe, we have to go above the Earth's atmosphere. And this was done first time when we had balloons a little bit, but more importantly, when we had satellites. So when satellites went up, then they could see this X-ray emission coming from different parts of the universe. It is for this reason that our story starts in 1970s. Before that, there were no satellites up in the around the late 60s when satellites came up, and that's how we came to know about X-rays. Now, you may have heard that of something called the Milky Way. The Milky Way is our galaxy. If you go up in a night sky in a clear day, you will see a band of stars in the sky. I hope that many of you have seen the Milky Way. And in this band of stars which you see, you will find that this is our very own galaxy. Our, our galaxy consists of many, many stars, and we are just one part of the stars. And what the band we see in the sky is in a different direction, and this figure along its center is the Milky Way. So what has happened is that when you want to represent the sky, you put the Milky Way along this central line out here. So all these sources you see, these ones which are very bright sources in X-rays, they're all sources within our own galaxy. And let us, for example, call them X-ray binaries. It's just a name. We'll come to details about what it is later. What is so special about X-ray binaries? The idea of X-ray binary is that the energy output.
Hey, Ranjeev.
Yes. Sorry.
Ranjeev, can you hear me?
Yes, I can hear you. Hello.
Hello, Ranjeev.
Yes. Yes, I can hear you.
Ranjeev.
Yes,
Ranjeev, can you hear me?
I can hear you.
Hello, Ranjeev, can you hear me?
Hello.
Ranjeev, can you?
Yes, I can hear you.
Okay, so yeah, so your slides are not changing, Ranjeev.
Oh, but it's changing for me. So okay. Can you see the slide change now?
Continue, Ranjeev, continue.
Hmm? Oh, okay. So sorry for the interruption. There was this issue that maybe my slides are not visible. So I've gone to non-slideshow mode. I hope that is slightly better. So if it's changing for some people, so let me start again from the current slide and go ahead. So
No,
no, so I should go back to.
continue, continue.
Uh, okay, so sorry for the interruption. There was. Okay, so let me go back to where I was, and the X-ray binaries have they produce about 10,000 times more luminosity than the sun, which is quite amazing. That if you look at some of these objects in the sky,
Ranjeev,
yes, yes, yes. Let me go back to where I was. And the X-ray binaries have hello. Hello.
Hello. Yes. Yes, sir.
Yes. Can you not see my slides?
Yes, is visible.
It's visible, right? So I should
Yeah.
starting from the first slide, right? I mean, from the in the full screen mode is visible, right, Sagar?
Yeah. Yeah.
Okay. All right. All right. So the X-rays from the sun. Can you not see my slides?
Yes, is visible.
It's visible, right? So I should on uh, okay. The When you look at these X-ray binaries, they are very bright sources, and they are about 10,000 times that of the sun. That is the luminosity, the amount of energy coming out of the sun, coming out of these each of these objects is 10,000 times brighter, more powerful than the sun, which is there. That is not a very surprising thing if you look into it. It is. It could just be a very large, big star, and there are many big stars in our galaxy and our universe which are much much brighter than the sun. So there is nothing very strange about the fact that these sources are 10,000 times brighter than the sun. But a strange thing comes out that we find that they are variable in milliseconds. Let me explain what variable means. It's like these objects are like flickering. Flickering is like if you have a candle which is in a slight breeze, the candle will flicker. It will keep going on and off in the uh, uh, keep going on and off. And this flickering is uh, very strange that these X-ray binaries or objects are flickering. A candle flickers in a time scale of let's say a second, but these objects are flickering in time scales of a millisecond. Now, if I tell you that the sun will disappear in 1 second, you know that that is not possible. Something as big as the sun can never ever disappear in a second time scale, right? And but if I tell you that a candle, we can just blow on it and it will disappear in about. You can shut it off a calendar or puff it off in a second. There is a general physics idea that small things like candles can change very fast, but big things like the sun cannot change that fast. In fact, we can put this in a physics law and say that if an object is a variable in, let's say, in a time delta t, then its size must be smaller than the distance traveled by light in the time scale. For example, if we can take a candle and you can puff it off in 1 second, this statement only means that in 1 second light can travel 300,000 kilometers. So the candle is smaller than 300,000 kilometers, which is not a very great statement at all. But look at that statement when we bring to these objects. Here is an X-ray binary, an object, which is 10,000 times brighter than the sun, but it is variable in milliseconds. In milliseconds, it's variable. So in that means light travels only 300 kilometers in a millisecond. So this object is only 300 kilometers in size, less than the size of, let's say, a state of Maharashtra or something, but it is 10,000 times more luminous than the sun. What strange objects could this be? Is the question. Before we address that, let's go back to the Skyview map. And these objects which you have seen here, these were called X-ray binaries, which were objects in our galaxy. There are many, many other objects in the sky, which is called active galactic nuclei. These objects are not in our galaxy. In fact, they are in the centers of other galaxies. There are millions and billions of other galaxies, and these objects are in the centers of other galaxies. In the thing. And they're active. They're very bright in X-rays. The total amount of energy coming out of an activated nuclei is 10 times that of a galaxy. Let me remind you that a galaxy has 10 to the power of 11 stars. That is 10,000 billion stars. But a single point source in the center of the galaxy is 10 times more than that of the galaxy itself. And even though it is so bright, they're variable in minutes. In hundreds of seconds, they change times. In hundreds of seconds. And light takes 8 minutes to go from the sun to the earth. So this object, which is 10 times more than a galaxy, which is 100,000 billion times more than the sun, in power and luminosity is less than the distance. The size must be less than the distance between Earth and Sun. So these objects which we find are very compact, very small, but very powerful. What could these objects be? One, the first thing to find out is how are they powered? What kind of energy are there in their system which produces this kind of power in the system? One important power we know is the nuclear burning, nuclear fission. So this is how the sun produces energy. But and we have read about this in the school. But this is not by far the most powerful source of energy in the universe. The most powerful source of energy in the universe is gravity. It is if you throw a stone, if you let's say if water falls down from a dam, that water falling down can be converted to electricity because of the gravity of the earth is converting that potential energy of the water down to energy. If you throw a stone from outer space to earth, it will hit the earth very hard, and that is what happens in meteors and showers, and can be quite damaging to the earth. However, uh, if you throw a stone to the sun or Jupiter, the damage actually is more because the stronger the gravity, the more the energy which will be released. Now, if you imagine that if you take a stone and throw it towards a black hole, the amount of energy it will gain as it comes closer to a black hole is very, very large. So, in fact, by throwing stones and particle mass onto a black hole, you can produce a lot of energy. Hence, strong gravity is the most powerful source of energy in the universe. So, I want you to consider two major factors. X-ray binaries and activated nuclei seem to be powered by strong gravity, and they're very small and compact. So here are two objects, X-ray binary. They are very powerful and they're very small. And the only way I know how to produce so much power and yet be so small is if there is something like a black hole in them which has very powerful gravity and can produce the energy. This is called the luminosity argument. I'm not sure how many of you would be convinced by this, but not many people were convinced by this. But this was the first fundamental argument that what we are looking at on these objects are black holes. Here's a drawing which tells you what is really happening in the systems, and that is in the center of this red object which I'm showing here, which is called an accretion disk. Deep in the center, there's something called a black hole. There's a black hole right in the center, in a small pointing. Now, this object here is like a regular star, and this regular star is going round the black hole, and matter from the regular star is being stripped off and falling towards the black hole. Since this regular star has angular momentum, this matter also has angular momentum, and hence it will go around the black hole in circles. It would go around in black holes in circles forever if it is not for the fact that this is hot gas, and hot gas has something called viscosity or friction, and because of this viscosity and friction, it slowly spirals towards the black hole. As it spirals, it forms an accretion disk, and this is what we call an accretion disk. And as it's spiraling, this disk becomes very, very hot. It's so hot that it reaches more than 1,000,000 degrees, and that is why it gives out X-rays and emission, and that is what we see in this object. This is a very beautiful picture, but there's one problem with this, that this is a painting, a picture. It is not reality. This is what we have imagined how things happen. How do we know that all this is true and whether such exotic objects exist or not? What we need to do is to see a real photograph, and let me show you one more real photograph. This is a very old photograph from the Hubble Space Telescope of a galaxy which is very, very far away, and we're looking at a real center of the galaxy out here, and what we find is a ring of matter going around it. this ring of matter, we can figure out that it is actually moving, it is rotating around an object, and by the speed of its rotation, we can find out how fast it is going. And by finding out how fast it's going, we can find out that there must be a very big object in the center, and that big object is a black hole. While all these evidences you may think are interesting, but they are not. They don't seem to be convincing. I'm not sure whether you're really convinced that there are black holes in the universe. So we need to have more concrete proof. One of the issues which has always been is that black holes are far away, and we are, for example, this image we are looking at a galaxy which is very very far away. The question is, why can't we look at our own galaxy? Why can't we look at the center of our own galaxy and see if there's a black hole there or not? There were two major problems in this. The first major problem was that the center of a galaxy is covered with dust. The universe is a very dusty place. In fact, it's a very dirty place. And the center of a galaxy is actually really covered with a lot of dust and things. So it's difficult to see through it. But using infrared emission, we can go and see through the center of the galaxy. The other problem is something called twinkling stars twinkle. So if we are looking at any part of the sky from the Earth, the atmosphere of the Earth distorts the image. That is why stars twinkle, and that is why we cannot see a very sharp image. To see a sharp image, we have to go outside atmosphere, and that is why we had the Hubble Space Telescope. However, the Hubble Space Telescope is a very small telescope. It's only 2 meters, and hence can't see deep into space as much as we can if we had a very big telescope. So it took a lot of work for people to do something called adaptive optics, and it took 5-10 years of hard labor. So what they do is they shoot a laser light up into the sky, atmosphere. This laser light reflects back, and because this laser light reflects back, we can now see what the Earth's atmosphere is doing on the top, and by that we can correct the Earth's atmosphere factors. And by this technology, we can actually go and see the center of our galaxy. This took about 15-20 years. It was very difficult technology to do. And in 1992, as this marks here, we finally were able to see the center of our galaxy. The center of a galaxy, as you see in this figure, is marked with this cross here red. Of course, we don't see this red mark. This red mark is just what I have put here. Is the most boring place in the universe. What you see are just 1, 2, 3, 4, 5 stars, and these 5 stars here, and these 5 stars are the most common garden day variety stars, which are found everywhere. So there's nothing interesting about these 5 stars at all. So the center of a galaxy is actually a boring place. There's nothing there in the center of the galaxy. However, science works in slow and difficult means. So, and I have promised you that I will not show you any more paintings or pictures. So what I'm going to show you is a real images. While this is a real photograph of the center of the galaxy, all I'm going to do is I'm going to show you a series of them. This, if you can see this image being drawn out, the left hand side is a date. All this is just photographs taken at different dates. And what we find is that the stars are moving. And they're not moving haphazardly. They're moving in a certain way, in a particular manner. Especially this star, which forms a beautiful ellipse out here along the red point. And if you have shown this thing to a person called Kepler about 300 years ago, he would have known what this is because the laws of these motions are named after him. called Kepler's laws. While Kepler was talking about planets going around the sun, here we're talking about stars going around something, and something unknown. And it takes only high school physics to understand and do the calculation that if you go through this kind of a calculation and find out what should be the mass of this object here, that mass of the object turned out to be about 2 million times the mass of the sun. So this, there is a black dark object sitting there which is not emitting in very very faint, but it is 2 million times the mass of the sun, and it is in the center of a galaxy, and this is considered as an amazing proof that this is a black hole. So by this time we could consider case to be closed and everything done, but people were still not satisfied. People wanted to see more information on the things. So if I go back to this image, one of the problem with this image, this photograph being, is that although the black hole is still very very small. We have not taken a photograph of the black hole yet, and it would, to take a photograph of the black hole, you would need very very good angular resolution, and it took a long time for people to do this, but finally in about 2 3 4 years ago we were able to actually take a photograph of a black hole, and this is a famous photograph of a black hole in the center of MA2, in MA2, which is nearby galaxy, and you can see the black patch here. This black patch represents the event horizon, and from there we know that this is a black hole in this. After this discovery, there was no doubt that there are black holes in the sky, and if there were any other doubt, this was completely shattered in a resounding way by the detection of gravitational waves, where now we can actually see two gravitational waves. We can see, we can hear, as we people say, the gravitational waves uh, of two black holes being merged, which was discovered, and now we are certain that there are black holes in the universe. Before I go to astrosat, let me go back to this painting and note here. Although I was talking to you about all the evidences that we had about getting black holes and all, the number of mysteries about black holes have increased greatly. You see this in this image. You can see this blue light things which are coming out of it. These blue things which are coming out of it are called jets. We have no idea what these jets are all about. We don't even know what they're made of. We don't even know whether they're made of protons. Don't even know whether they're made of electrons and positrons. We don't know how they are produced. We don't know what is the energy, what is the energy source, and we have known them for 30 years. You see that, like I said earlier, that these systems flicker in time, they vary in time, and that is why how we knew that these objects were very small. But why do they flicker? And because they flicker, we know that they're happening close to the event horizon, the black hole. All this variation. But why is it happening like that? What is the nature of this variability? We have no understanding of that either. To understand all these things, we have, about 5 years ago, India launched AstroSat, and the primary purpose of AstroSat was to understand the variability of these black hole systems. We have now collected a large amount of data, which I will not talk about because if right now from AstroSat, and this has really enhanced our understanding about how black holes vary, why do they vary, where do jets come from, what are the things, and there are many many mysteries which we are solving now that we could not solve earlier, right? So AstroSat has spent 5 years. Now India is planning to launch another satellite in another 5 years, which will be an ultraviolet satellite, which will again look at such kind of objects like black holes and all, and discover more new great things about them. There are international satellites which are being launched. There is one beautiful instrument above the space station, on board the space station, which is looking at the variability of these black holes very fast. And so, in and we have the gravitational wave detectors which are detecting these black hole mergers. So there are lots of things which are going to happen in the next 5-10 years. But what we need is people to they allow. Although we have seen a lot of things, the number of mysteries have become larger and larger and larger, and we need people to look at these objects more, and more importantly, to explain to us and understand and unravel the mystery of this universe. So now I will thank you for listening, and I'll stop here, and I will uh, see if I can take some questions if possible. Hello, hello.
Yeah, so there are few hands are raised,
Yes. Uh,
people. So
uh,
I will just announce one by one and unmute them.
mhm.
So first, we have take the question from the Sen Gupta.
Yes.
So I'm unmuting them.
Okay. Yes, Sangram Sinut, let me hear your question.
Good afternoon, sir.
Good
Am I
afternoon.
audible?
Yes, you are audible.
Oh, thank you, sir. Sir, actually, I got two questions. First of them is that how is the event horizon forms? What causes it to be formed, or what is the limit that marks the event horizon? Is there anything such that?
Okay, what is the second question?
Second question is that sir, black holes are actually spherical objects, as far as we know. So, how come this accretion disk which are forming is forming as disks and not as spheres surrounding those black holes?
Okay. Uh, uh, I, I think you can still see my screen, so I will uh, go ahead and answer your second question first. The second question, interesting thing. Let me repeat the question for people who may not have heard it properly. The idea is a black hole is a spherical object, it's a sphere. But in this image, what I'm showing is that there is some kind of a disk which is non-spherical going around. Why is that? How is it that a spherical object can produce a disk which is non-spherical? This is because, as you see, there is another object here, the star, and the star is going around the black hole. This forms a plane of our system. The star, the black hole, and this thing. So the star has angular momentum, and angular momentum has a direction of the plane. So the matter falling in from the star will form a ring, and this ring will have an orientation and a long distance. So the star, this disk is formed along the line joining the star and the black hole. I hope that was clear. Now I'll answer the first question. The first question is that how does an event horizon form? The interesting thing to note is that if we believe in Einstein theory, and if it is probably true because we have not seen it, we will never see an event horizon forming. As a star collapses, we will just see it becoming blacker and blacker and blacker and going. If you fall into a black hole, you may go and see into an but I know there are many movies, there are many books, many things about falling into black holes. Let me assure you that falling into a black hole is not part of physics. There's a very good reason for that. Physics is a study of experiments. I will come in my next talk tomorrow. I'm going to emphasize this very importantly. If you take an experiment and you drop it into a black hole, you will never know the result of the experiment. Since you never know the result of the experiment, that is not going to be a scientific part of it anyway. So to answer your question, Januk, if I'm looking at a star collapsing, I will just see it becoming blacker and blacker and blacker, and and I will theoretically expect it to form a black hole. I mean, an event horizon. And to answer the second question, this is the accretion disk is along the line joining the star and the black hole. Okay. All right.
Thank you, sir.
Thanks. Okay.
So next question is Shah. Unmuting him.
Yes.
Hello.
Yes, Himadri.
Sir, my question is that, sir, is gravitational lensing can be taken as an observational evidence for black holes? And how can we characterize the properties like the size of the mass from the lensing properties?
Uh, I will repeat the question for the benefit of others and answer it. The question is gravitational lensing. Has there been evidence for black holes using gravitational lensing? First, what is gravitational lensing? Gravitational lensing is the bending of light. So, if you have an object like the sun, it can bend light, and anything that can
Yes,
bend light will act like a lens. So, therefore, it's called a gravitational
yes,
lensing. Now, when we are, there have been many searches for black holes. We have seen gravitational lensing from our own sun. We have seen gravitational lensing from galaxies. I mean, galaxies which are acting like lenses, which are bending light. So any matter can bend light. So we have seen this bending of light by matter for many various objects. We have searched a lot for looking at bending of light by black holes. Unfortunately, so far we have not ever found a very convincing case that the bending of light we have seen or some lensing we have seen is definitely from a black hole or not. That is because black holes are very, very small. So, for a black hole to act like a lens, it must be in front of another object. Now, since black holes are very small objects, it's difficult for them to be in front of other objects, and that is why it is we have found it difficult to see gravitational lensing by black holes so far. Okay,
thank you, sir.
thank you. Okay,
Okay, so next question is from Soumya Mandal. So I'm unmuting her.
yes, please.
Hello, sir.
Yes, Samya.
Yeah, the question which I had, basically, sir, I had two questions, and the first of all is that how can these jets escape the gravity of the black hole? And secondly, are there any sort of predictions which we can make about what lies beyond the event horizon of the black hole, or how a black hole distorts the space-time curvature if any of that sort of thing happens?
Okay, so there were two questions. Actually, there were three. So let me repeat the questions again and go. The first question is, how do the jets
Yes.
come out at all?
Yes,
Obviously,
sir.
jets cannot come out from inside a black hole because that's not allowed. So jets have to be coming out from close to the black hole, but outside. But why are they coming out at all?
Okay.
At all is a question. If we answer, if any one of you answers it correctly, I will be very honored to nominate you for a Nobel Prize in physics. In other words, we don't know. There are many
Okay.
theories
Yes, sir.
about this is one of the biggest mysteries. There are ideas about how magnetic field pulses can go out, and how there are also ideas about how magnetic field interacting with the spin of the black hole can push jets out. How, but none of these
Yes, sir.
things have been at all been convincing enough or to say that this is the real mechanism for it. Right. The second question is,
Yes, sir.
what can we see what happens inside the event horizon? What happens inside the event horizon, like I'll talk about in detail tomorrow again, is not part of physics. Again, I'll repeat that if it can be part of philosophy, it can be part of movies, it can be part of imagination, it can be even part of mathematics as a subject, which it is, and people do a
Okay.
lot of mathematics. But it's not a part of physics because physics is based on experiments. And if you cannot do an experiment on a object, I even what you call a thought experiment, at least, because once you go in a black hole, even though you can't do any experiment and you can't exchange information, what happens inside a black hole is no longer part of physics. However, you also mentioned about curvature of space-time. The curvature of space-time occurs
Yes, sir.
even outside the black hole. The very close to a black hole, the space-time is very, very
Definitely.
curved in space. And this we are slowly unraveling. We are finding direct evidence for this curvature of space-time over matter. First, we have found evidence, obviously, as you see from the gravitational when gravitational waves when two black holes merge. We know that from the signal of waves that it merges. More importantly, I told you that light gets gravitationally redshifted as we are close to a black hole. We have started measuring this gravitational redshift. This gravitational redshift directly measures the curvature of spacetime, and we have been able to figure out, in some extent, how spacetime is curving. We are we have been able to show that some of the predictions are matching with those of Einstein's theory. However, I must add that it is still on a very preliminary stage right now. We need much more information to get a detailed understanding of the curvature of space time near a black hole. Okay. All right.
Okay. I guess we have finished all questions who
Okay.
has the hand.
Okay. I will then, because it's getting late. It's 11:35. So
Yeah.
I will now stop this, and I'll take the questions from the YouTube things.
Yeah.
I'll request the YouTube people to send me a question. And if you have pressing questions, you can please also send me an email. And uh, I will not tell you my email address. In this modern age, you can easily find my email address and the correct one that too. And please send me email and the questions, and I will try and answer them. It may take me a few days because I may be traveling. I may be busy working, but I will answer your questions on email when required. Okay.
Okay.
Okay. Uh, all right. So we can stop it here, and I'll be back again tomorrow, and hopefully tomorrow things will